study based on the different locations possibles with the grid. Am I audible?
Yes, sir.
Okay. So before starting my presentation, I would like to give a brief introduction about my institute and initiatives in the area of renewable energy by my Institute of DEI. So we have as seen in the first figure, we have a large size of solar rooftop mounted solar system at the various buildings of the DEI. And then we have a solar agri farm for in which we have done the research how the agriculture can be done under the pole mounted sun tracking based solar systems. So this project was funded by the DST and in collaboration with IIT Roorkee. Then another, we have a solar thermal cooking systems which we use to cook the food for the students who are staying inside the hostels in our campus. Then we have the solar power plants in our, because DI has the multiple centers which are located in different locations in India. So this is one of the plant which is installed in our one of the remote centers over there. Then we have a solar wind hybrid systems. And this is the another one is the proposed one e-vehicle charging is infrastructure which can be used to charge the vehicles nearby highways. So solar panels and wind power plants can be installed near the highways. These are my books which are published. First one is published by the elsewhere in distributed energy resources in microgrids, integration challenges and optimizations. And another one is the microgrids for rural areas research and case studies published by IIT. And third one is being instrumentation engineers. I have also worked and my team is also worked on the medical image processing and diagnosis. So this book is also published by the elsewhere. Now come to the point of the topic of the today talk. So worldwide here in this image, we can see the global access to the electricity, or we can say the various users or the location wise, how the electrified the area or the earth is electrified globally. So here we can see that the light color, like the light color is representing yellow color is representing that the completely area is electrified and well connected with the grid. And as we can see the dark locations, various dark locations here as shown here. So in this we can see these dark are representing that the grid is either not connected or connected with for very limited hours of the day. So these are the main challenges, how to electrify these sites, or if the sites are connected with the grid, like these are a little bit dark yellow or different colors is there, red is there, black is there. So how, if the grid is connected, how we can increase the system reliability? Okay, so based on the current scenario, 16%, approximately 1.2 billion of the world population are still living lack of electricity access globally. If we talk about the reliability of the grid electricity, connected households, so these are the various locations in the African countries. So here we can see like the based on the color coding here, the yellow is representing that the most of the time is away from the grid, and then we have the never available, and then we have the occasionally half of the time. So based on this, we can see the various locations. So here we can see like the grid is in most of the cases, the grid is not available 24/7. So how we can increase the system reliability, how we can fulfill the sort of demand during this, because this is it may be the cause of sort of energy or sort of demand, means power. So like we may have a, for example, we may have a requirement of 100 megawatt hour, for example, I'm checking, and our plant, so this is the energy consumption, but the plant installed is producing this electricity during the next 24 hours, but at particular time instant, or we can say the maximum rating of the power generation of the particular plant is, for example, it's uh, 2 megawatt or 2.5 megawatt. So the energy demand is fulfilled because 2.5 will be multiplied by the 24. So it will be greater than the 100 megawatt hour. But the power consumption at particular time instant, if the power is 5 megawatt, power consumption is 5 megawatt, so due to this the grid may be overloaded, and that's the cause of the load shedding to maintain the power inside the grid. So this is the reason like why we are facing the uh, um, grid is occasionally available for us while we have the grid connections. Okay, so based on these, I have done the various studies. How can we fulfill or how can we mitigate this type of challenges? So this is our traditional power systems in which we can see here like the power plant is very far to the load, and it means we require the multiple transmission lines. Then the step up or step down configurations like substations are there, and then the large structure of the transmission lines. So all these like conversion and the way or the path to transmit the power from the generating station to the receiving, and there are multiple losses. It may be in the conversion, it may be due to the line losses. Okay, so if we are able to minimize these power losses, or we can save the power losses which are occurring currently in the transmission lines, that may increase the available power to use for the customer. And the another, either increase the power plant size far end and then connect with the uh, to the load through the different distribution or transmissions lines, then it's required the huge infrastructure development, as well as it will further increase the losses. So the another solution may be like we generate the electricity nearby the load, and so that this infrastructure is not like the further expansion of the infrastructure may not be required, or required in a little way. But if we increase generation here, as we can do with the renewable energy resources like solar power plant or the wind power plant, which can be installed here, but for that, we require the alteration or changes in the distribution infrastructure, because our system is designed for the power receiving at the load and not to feed it to the grid or send it back to the grid. Okay, so the alteration is or the changes are required here. So, based on the classification of the sites, we can classify based on the grid availability. So, one is called like the isolated site, like the grid is not connected to particular location. Okay, then another may be the grid connected sites, like we may have uh, a semi-urban or the urban areas where like the grid is available, but like where the grid connected sites can be like further classified into two category. One is the high reliability, means we are considering the grid is available for 24 into 7. Like we can talk about our metro cities like Delhi, Mumbai, particular locations which have the grid available for 24 into 7. So further, we can classify these high reliable sites into two category. One is like the electricity price may be fixed like not varying with respect to time, and another one is the like prices are varying with respect to the time, or prices are dynamic. Okay, like the user may be the residential or maybe the industrial. Okay, then we have the poorly grid available. So the grid is available for few hours, as I have shown the in the previous slides, that the grid has the particular location or the particular consumer has the grid connections, but the grid is available for limited hours. So it may be the another case of study. Then if we talk about like the what can we optimize, what type of research can be done here. So based on this, the optimization of various sites based on the uh, thing, like the isolated sites, like if the grid is isolated particular site and we want to electrify that area, so what could be the optimization parameter? So optimization parameter may be like the energy losses in the system, like it may be losses in the conversion, it may be the losses in the lines. So how we can optimize that? That may be the one area of research for the scholars. Then another one is the source size, like if we are electrifying the particular remote isolated site, it means we have to install the distributed generations over there. So which type of generations, so generating source we should, how we can electrify the particular site without installing the large size of a power plant, or their size can be optimized. The next one is based on these two, we can further optimize the cost of, because if we will install the random size of the solar of the distributed generation, it means we may require the large size of generating units, and if the large size of generating units means we require the, we have to put the high capital cost. Then if we talk about the grid, means the grid is well equipped with the power generating units as well as the load is also balanced. So the electricity cost may be the concern over there, because the system is already installed, everything is there. So how we manage different sources to optimize the electricity cost. Okay, like we may have a, to supply particular locations, we may have a like a hydropower plant, we may have a thermal power plant, we may have the renewable energy resources. So we may have like fuel based generating stations. So which generating station we should run at particular time stand, so that we can fulfill the energy demand, power demand, as well as the cost of the electricity. That may be the one type of case study. The another one is like the poorly grid available. So in this case, like the grid is not available. So I hope um, many of you may have the inverter inside your house, because the grid is available for few hours. So remaining time you have installed the uh, inverter in your house, so that the appliances in your house can run during the outage of the grid. So in that case, the size of the storage device, like the battery bank or other storage devices, is the concern of research, how we can optimize this one. Then the size of the internal resources, like you may have a different distributed generation, you may have the solar rooftop mounted solar system, you may have the small wind power plant, or you may have the fuel generators at your home to supply the residential load when the grid is not available. So how we can optimize this size? This is also the area of research interest. And then the capital and running cost. So in all the cases here we can see the either the capital cost will vary, or the running cost, in case of like if we have a generating station which are based on the fuel, like the thermal power plant. Okay. Now
So to overcome all these problems, the governments of in India as well as in abroad, the governments are pushing to install the distributed generations, uh, which at the different location. It may be the solar or the wind power plant. Okay, but might be the example of combined heat and the power or thermal generation based on the biomass. Different type of generating stations you may see at different locations in India as well as in abroad. So let's consider this is the example as shown in the figure here. We have a grid connections. Then this grid is connected with the particular local sites with these two transformers, and then we have a connections uh, with the wind power plant and the load. Here we may have a load of particular industry and the load capacity is 7 megawatt. Peak load of the industry is 7 megawatt and the capacity of the wind power plant is 15 megawatt. If we talk about the line capacity, this is 9 MVA. So we need to manage the system. If we'll cut this load completely, then this wind power plant cannot, power generated with this wind power plant cannot be fed to the grid through this line because this line capacity is little bit low. So how we can manage all these things? That's the challenge for the utility to install the system in an appropriate rating. For example, here I have considered example number 1, a 15 megawatt wind power plant installed at a connection C, because it can be installed at different locations. So we have considering that the wind power plant is installed at location C. If the reinforcement of the line between B and C is required, we want to change the line. So what if we knew that the minimum demand at C is 4 megawatt at the place of 7 megawatt? If this plant is dropped down up to 4 megawatt, so who will take care? It means the 11 megawatt will be the surplus generation and the rating of this line is less than that. It means we have to do the curtailment of the power generation from the wind power plant. So what account can be taken in real time? How we can manage this system? What are the things we require to connect with this system? Because here I'm showing just the uh, infrastructure same like a traditional power plant, traditional grids. Okay, we have like generating station, load, etc. Now, to overcome this problem, increment of wind outage, like by just enough, or these two things are enough, or we need to do some other necessary things we need to do. So like here we have a wind power plant, minimum load is 4 megawatt and we have a 9 MVA ratings of, and this is our transformer. So if we talk about the curtailment of these, like the power generation with the wind power plant, and if we curtailment this generation to manage the power or to balance the power in this line. So here we can see the cost versus the boundary transfer capacity. So like this is for the cost of curtailment of generations with the wind power plant, and this line is representing the cost of reinforcement of the line of this line. And here based on that we can find out the, based on these two curves we can find out the optimal boundary capacity or total cost which can be. So based on that the options can be opted out, like which how much we should do the curtailment and how much the reinforcement cost can be. Now, possible solutions may be like the wind power plant pays for the enhancement of line rating. Then we have the like the wind farm installed less the wind turbine size. Like at the place of 15 megawatt, can we install the wind power plant of a lesser size, like the minimum, if the minimum load is 4 megawatt, so 4 plus then the convert it into the megawatt, the line rating, and then based on that we can select, okay, this much size of the wind power plant can be installed here, and the remaining can be added at the location B here. So for this, or we can do the another thing is a small smart network management SNM systems is installed to manage the period when the line would be overloaded. Only that time the curtailment can be done. Remaining time, like if the peak load is 7 megawatt, here is the capacity is 15, so 8 megawatt we need to feed it here, and if that is feasible, so we can feed it back, and sometimes we can take it from the grid. Based on that, the smart network management can be done, how to manage the all these both the sources to fulfill the demand of this particular load. Then how much energy would be curtailed? If we are talking about the curtailment of this, how much? So how much income does wind power plant lose if we are reducing the generation? If the uh, wind power plant has installed the size of 15 megawatts, so how much may be the loss here? And whose responsibility is to make a estimate of all these things? Either the wind power plant owner or the utility who will take care about all these losses, etc. So now the option may be like the integration of the wind farm at sea does not have the fire farm connections, or it is not n minus one user secure here. Like we have a 15 megawatt here, and we want to further increase our generation because the rest of the grid is required the surplus or more generation to fulfill the energy demand of the nation or the energy demand of the globally. If we are exporting the electricity with our neighborhood countries. Okay, so like let us consider we have a 15 megawatt here, 15 megawatt here. Still the line capacity is 9 MVA, peak load is 7 megawatt, and here the transformer capacity is two transformer and each capacity is 10 MVA here. So here we can see that the 20 MVA is the rating of these two transformer to exchange to feed in or import the power from the grid. So here we have the 15 megawatt, then 9 megawatt, 9 is here, around 8 megawatt will be here if we considering the or 7 megawatt will be here if we consider in the 0.8 power factor. Then so 7 plus 15, 22 is still here. The rating of the transformers are only 20, so it will these transformer may be overloaded. If we are feeding it back, then the management is required. Okay, so let's consider line CB is okay. Like in this case, we may have surplus generation here, but the 7 is there. So this line is able to take care the power generated with this power plant to the grid. But this area may be the problem because here the maximum capacity of the power exchange is only 20 MVA. Now let us consider the another example, possible conflicts between the transmission system operator and the distribution system operators. So what if the same time DSO wants to reduce the distributed generation output to avoid the overload of the lines? Like we have considered this line and this one want to decrease their generation to balance the power in this line. Okay, and the TSO wants to reduce the demand or increase the generation because the utility wants the more generation or want to curtail the generation curtail the load at particular location. So how will balance increase the balance out of the whole system? How will manage this system? So export the line thermal limit will be the constraint here. Then the increase output at that particular locations can be done. Like if the limit is allowing, so just increase it further and increase the output here and then start feeding it to the grid. And if this is not, then keep your system stable, and the rest of the things need to be taken care by the utility. So the optimal network capacity is not like the constraint free. Again, like the constraint need to be smartly managed, and the constraint management depends on the observability and the controllability of the system. So this is like the cost of reinforcement and then the cost of curtailment, and based on the optimal network capacity would be like here. Some we are just doing the curtailment of the power generations, and the cost of some plants may be connected with the additional lines, etc. And based on that, the optimal locations may be somewhere here, B or A, depends on the fit and forget network capacity method. Now, next, maybe like the, if we talk about the residential areas, so the poorly grid connections, like here we may have a like grid is available for few hours, as I mentioned, as I've classified the different locations in the various based on the grid available. So here first maybe the grid is available for few hours. It may the location may be the rural or the semi-urban areas, right? And does not open for power feed-in. Like this is the situations. We have the solar power plant on the rooftop, but we cannot feed it to the grid. So this is the one situation, like the situation like we have the loads and we have a solar power plant, and each house has the solar power plant. Installs less. Based on that, the user may decide it like how much, or the prosumer may consider like what could be the optimal size of the PV system for me, so that I can minimize the running cost of my system as well as the capital cost of my system, and minimum curtailment can be done. Then the smart management may be there. Like here we have the multiple houses, all are connected through this bus. So the power exchange can be done locally with these houses. If the like power requirement here is less and the generation is more, so can we do it? Can we share this power with the neighborhood houses? Okay, then we can also do like the demand side management, like some appliances inside the house may be differable from one time instant to the another time instant, like for example, washing machine or water pump, etc. So these may be, or we can install some energy storage. So energy storage may be in a different form, like it may be form of hot water, which may be required during the night times, or in the early morning, or the late evening, or the different time instant depend on the weather conditions. So it may be stored in as a hot water, or it may be stored in the chiller to cool the particular locations. So based on the weather conditions, we can store the energy in a different form. It may be stored in the form of electricity inside the battery, or maybe stored in the hot water in a geyser, or it may be stored in the chiller, and later on that can be used. Then the another type of challenge is like here is, as I mentioned, that our traditional system is designed for one-way power flow, like from generation or the transmission to the distribution. And so here maybe the situation like we may have a multiple houses, and these multiple houses are connected through that particular transformers. So it was the earlier situation, but now the things are changing. The consumers are installing the EV charging station at their own home. So now the load is increasing on these distribution transformers. So here we can see the data. 64% electric cars are expected in US by 2030, according to the study commissioned by the University of California. Okay, and the electric customers will measure that electric car into the garage plug-in. They can anytime connect the grid, connect the EV charger with the grid anytime. It may be daytime or in the night time. So if the whole load if we are saying that the peak demand of this house is already running, and the user has also added the EV charger, so the electric grid may be like the load on the electric grid of particular user or particular consumer may be double. Okay, so the electricity distribution systems comes a significant new loads and wasn't be designed. This system wasn't designed for it, because like for example 5 kilowatt of each house is now the 5 kilowatt load is also come into the picture, that is EV. So we need either they need to alter the lines, or they need to alter the distribution transformer, because it may be overloaded, because this transformer were installed based on the load of these houses, or we can say only these 7 houses. But now out of these 7 houses, 6 electric vehicles are also there. Okay, so that's the another challenge. The example number 4, like the electric car in a condensed area are plugged in overnight over, and if you are fast charged, like we may have a different types of charger, like MG is providing 2 types of charger for the electric vehicle. One is 3.3 kilowatt and second one is 7.5, while the Mahindra is providing up to 11 kilowatt rating. So if the fast chargers are there, so maybe that the EV load act as a double as compared to the house load. Okay. For most utilities, the delivery system can accommodate these new loads if it's evenly distributed. If we if this house has the higher load, and if this customer is not at home, or they can wait for the next their turn based on the price or based on the monitoring of the power, utility may send the signals, okay, at that time the distribution system is overloaded, can you wait for the next few hours, so that, like, can we schedule the charging of these vehicles in an alternating way, or in 24 hours can the utility send the information to the consumers, okay, just charge your vehicle, wait for to the rest of them, they may say, okay, just wait for the first slot, then you can charge in like this. So in this way the infrastructure may be same, but the energy consumption has been distributed. But if all the vehicles, all the houses will be at the peak demand, that time we need to, or the utility need to change these transformers. Now, so because of this, the transformer may be overloaded. So clustering of EV vehicles could quickly over extended electricity distribution assets. Now, to put this into the perspectives, consider that the Nissan Leaf charging on a 240 volt 15 ampere circuit generates around 3.3. As I mentioned, like the MG is also providing the same type of 2 types of chargers they are providing. One is slow and second one is the faster one. Then we have the another configurations 240 and 30 amperes, so 6.6, or now in the Indian market we have a 7.5 kilowatt chargers. Okay. As the secondary transformer, which is located here, have been properly sized to accommodate the load of 10 to 15 houses. Okay. On average in India, generally this type of configuration they use. So here the size may be the higher one. Okay. If we talk about the various public charging, so here we can see that 2 types of, one is the faster one and second one is slow or moderate. Depends on the, like, first one. If we talk about first three, so we have like combined charging systems, minimum 50 kilowatt, and then we have the another one is the 50 kilowatt, and then the third one is the type 2 AC chargers 22 kilowatt minimum. Their rated voltage are listed here, and the number of connectors or the guns is here, and the types charging vehicles type, it may be the two-wheelers or four-wheelers. So here the first two is only applicable for the four-wheelers, while the third one type 2 charger can be used to charge the four-wheelers, three-wheelers and two-wheelers. Then we have the slow or moderate chargers here. So like the Bharat DC-1001, 15 kilowatt, then 15 kilowatt. But the rated output voltage is like 48, 72 and 230. And their use is here listed. So now, based on till complete presentation, we may, based on it, we observe that the need of a smart system is there. So which can, a smart system like which can operate in a grid connected mode, isolated mode, and able to monitor and control the integrated distributed generation as well as electric vehicles. And that point or that type of requirement can be fulfilled with the microgrid system. So what is microgrid basically? So microgrid, like here in this figure is shown, like microgrid consists of the distributed generations. It may be the wind, solar, or it may be the like generators, or it may have the grid connections, or it may also have the energy storage and load. The good thing is like it can work in, it can manage their sources and load locally, and then it may have a single point metering with the public utility. So it will first manage their internal generating stations as well as load, and then if the surplus generation is there, it may feed it to the grid. If the surplus load is there, it may consume the power from the grid. And based on that, so this is infrastructure which has like the intelligent control system with system optimizer, because in the previous first few slides I have talked about the what can be optimized in the different at the different locations. So like microgrid may be the grid connected or maybe isolated, so it can electrify the different sites, either the well equipped uh, or we can say highly grid sites which are highly reliable, or the poorly grid available or isolated. All these things can be done with this structure. Okay, so how it reacts, like we may have considered the we have a thermal power plant which is located far ahead, as I have shown in the first slide, the traditional distribution system or the complete infrastructure of the grid. So we have the generating station here, then we have the uh, load here, and then we have a power network which is connected with this, and then we have a interconnection with the locality, and this locality is also connected with the rooftop solar mount, rooftop solar plants as well as electric vehicles. Soon here in few house the electric vehicles is there, and this is also connected with the wind power plant and the solar power plant which is nearby to this locality here. Okay, so this is like acting as a microgrid, and the power exchange, this is a control here. So how the power will be, it will monitor the power generation here, and the load demand of this particular of this site, and then the power exchange decision will be taken. Either we need to feed it the power to the grid, or or the system is going to consume the power from the grid. The another type of structure of the microgrid may be like plug-in electric vehicle charging stations. So like we may have a grid and we may have a wind photovoltaic power plant. So this power will be fed it here. So if the grid is not available, that time this energy produced with this photovoltaic power plant will be curtailed. That will be the loss for the consumer, for the producer. So to overcome this, the another component may be added, like the we may have the electric charging station here, or ports for the EV charging. So here, if the grid is available, and the EVs are not charging, this surplus generation may be feed it to the grid. And if the grid is not available, this energy may be used to charge the electric vehicles. But still, the situation may be like the grid is also outage, means we cannot feed it the power to the grid, and the vehicles are also not available for the charging at particular time instant. Then what will happen? Who will take care about it? The solution may be like that. We may have the battery bank here, which may be designed to consume the power of this power plant, or the size of this battery bank may be optimized based on the previous data, that how long these vehicles are available when the PV generation is there, and how long this grid will also be available. Based on that, the size of this battery bank can be optimized. Okay. So the complete case study may be like this now. So the surplus generation is there. If the generation is from the PV power plant, so it can be used to charge the electric vehicles, and surplus may be either charge the battery bank for the future, and it may be fed to the grid. Depends on the, so multiple case study can be done with this type of structure. So now if we talk about the mm, if we talk about the remote utility projects fuels 2 gigawatt rise in the global microgrids. Okay. Capacity. So here we can see the microgrid capacity by market segments, world market. So here we can see like the remote systems, to electrify the remote systems, 691. And for the military applications, the microgrids are used 578, then commercial and industrial 327, then community level of microgrid systems are 669, and the institutional campus is 915. Okay. Then if we talk about the uh, percentage wise at the different geographical locations, so in Latin America we have 4% microgrid installs, then Middle East and Africa 3%, and then for the North America we have a 42, Europe 12%, and Asia is 39. Total microgrid capacity and revenue, world market, if we talk about during the 2017 to 26, which is going on. So here we can see like the North America, Europe, Asia Pacific, and Latin America, Middle East, and total revenue is so shown here. In 2017, it was just 2000 megawatt, while now it has been raised from 2000 to 12,000 megawatt. And here we can see that in revenue in the dollars, in millions, here we can see it was in 17, it was around 8,000 USD, but now it has been reached up more than the 50,000 USD. If we talk about the ranking of microgrid implementation drivers by the end user type, so here we may have different types of, we have the utility based, or as well as the uh, um, different location wise. So first maybe the like university R&D. So university, the primary incentives maybe the cause, or the ownership ratio is like 50%. 50% is the like the end user, and the 50% is the utility and municipality maybe there. Okay, so the purpose of the university, like the cost reduction of the running cost of the university and high reliability, because if the grid is outage, the labs and the campus electric may require the electricity, then they have to run the fuel generators over there. So they may have some stuck complete microgrid system as my university has. Like we have a different energy storage units. We have the solar power plants, and we have a single point metering with the utility. So we are also doing the R&D, and the emission reduction is the another constraint. So similar type of things maybe with the other university also. If we talk about the another component, this is military installation. So high reliability, critical is there, and we don't want the electricity outage for any time instant. So that may be the one concern. Then cost reduction, the cost of the complete project, and the less risky supply security and R&D, etc. It may be the another cause. Then now, if we talk about the like the city and community level, so reliability, maybe the like the prosumers, like the residential customers or the communities, they may be bothered about the reliability of the grid. Then the energy policy targets, like the utility or the government may push them to minimum produce their to reduce their load on the utility and defer the investment. Maybe like here we can see the few 20% maybe the end user and remaining maybe the utility based. Then the public institutions, so reliability or safety, cost reduction and emission may be there. So here the end user maybe like public institutions, the end user will install most of the, and the utility may or municipality may pay some amount of this or may provide some subsidies like government is providing for the residential customers nowadays on the solar power plant, etc. Then if we talk about the commercial, so cost reduction of the like industry want to reduce their running cost or emission reduction may be the target for them. And then the environmental uh, things. Okay. Then we have the remote community, renewable integration, and then investment is there and reduce supply risk, chain risk, etc. The percentage may be like here 40-60. And then we have a Iceland. The cost reduction means we are talking about the autonomous microgrid. So the cost reduction may be the constraint or the reduced supply chain risk is still there. And then the renewable integration. So here maybe like the 40-60, 40% by end user and remaining maybe the utility, and utility don't want to increase like infrastructure or transmission lines. They want to electrify that particular locations and want to connect with the small rating of the distribution or transmission lines for particular location. So here we can see like the impact of the battery on highly renewable energy penetrated grid. So here we can see like the battery, why the battery is there, why not the another things. So here in this figure we can see the earlier was like the thermal power plants or hydro-based power plants, and then the load were varying. In the initial case, the generation was varying, but now the but the load was fixed. But now, sorry, the load was varying and generation was fixed, or the generation is so based on this generation, the grid do the load setting, etc. Okay, but now the things are changing. So in the earlier time, we were able to just control the production of these power plants. But now the utility or the prosumers are installing the renewable energy, and their behavior or their output is varying with respect to the time instant. Like the sun is available in the day hours, and the output of the uh, solar power plant is varying at different time instant. In the early morning, the generation may be very small. In the peak day of the time, peak time of the day, the generation may be very high. In the evening time, further the generation is going to decrease. Similarly, the things may be with the wind power plants. So earlier only the constraint was here, but now the generation is also varying. So how we can overcome with this type of problem, so that we have a like energy storage there. It may be the large size of the energy storage to overcome this problem. So whenever the surplus generation will be here, it will consume the power from the grid and it will keep the grid parameters within limit. And if the surplus demand is there, it will feed it to the grid as shown here. So why the battery? Because its response time is fast, as well as it's not only the acting as a generating station, it can also act as a load. So it can support to the utility in both the cases, either the surplus generation or the surplus load. So now if we compare it with the others, so the fuel consumption. So here the problem is not the what rate you are like what's the power exchange. Based on that, the power exchange rating of the energy storage may be maintained. If we talk about the other sources, alternate for the battery storage, like if we want to do the curtailment of the uh, renewable energy resources, but if we want to run the generator power rating like different is here. If we run this 20 kilowatt generator at the quarter load 1 by 4, so how much like it will consume zero point 0.6 gallon per hour. If we run the same generator at half load, or the output is like 10 kilowatt, so the consumptions will be 0.9. And if they will run it at 75% load capacity, the consumption of the fuel will be to generate the same amount of energy is 1.3 gallon per hour. And if we operate it at full load, so the consumption will be 1.6 here. So if we want to generate some amount of energy, I'm talking about the energy. Okay, if we want to generate a 100 kilowatt hour energy, okay, but we have run this generator at rated load, okay, so just 6.4 gallon is sufficient and enough. And if we run this generator to generate the 100 kilowatt hour at half load capacity, it means the zero point 0.9 is there. Okay, so it means we have to run this plant for at the place of 5 hours, we run it for 10 hours. So here we required 6.4 kilowatt, 6.4 gallon is sufficient to generate the 100 kilowatt hour. But in this scenario, it will be like 9 gallon. So we can say how the running cost of the generators are varying. Similarly for the others, it may be if the quarter is there, then it will further increase. Okay. Efficiency of, if we go for the other power plants, so efficiency of various power plant is here, like hydropower plant, tidal power plants, and so on. We have it. So solar power plants is also their efficiency is listed here. Okay. Now the benefits of load following of battery. Why we are going with this? So the benefit is like the storage with a very fast ramp rate can provide the relatively ancillary services such as frequency response and area regulations. I hope the persons who are from the power system background, they know about all these parameters. Most type of generations have the slow ramp rate. Their output cannot be changed quickly. Okay, like in case of the thermal power plant. So the generation, if suddenly the hikes will be in 10 megawatts, so the generation may not be fulfilled with the thermal power plant. So that times we may require some storage or the hydropower plants or some other fast response. Okay. Then the storage used for frequency response and salary monitoring monitors the AC frequency and responds the for the like the battery can respond in very uh, small time instant like in milliseconds. Okay, the load following nature of the battery helps to reduce the need of the generating equipments like the other controlling devices, as well as reduce the generation output variability and part load operation of the generation is there. Reduce fuel use and air emissions is the another benefit of the battery load following phenomena of the battery. Reduce generation equipment wear and extend the equipment generation life as well. Now the ramping, like the battery benefits for grid operations. So ramping is there. So ramping in a significant change of generation. So power output over time frames ranging from a few seconds to a few minutes. So of a particular interest like the wind generation ramping that is caused by rapid wind speed. So if the like suddenly the variations in the speed of the wind, so the generation will rapidly high of the wind power plant or rapidly it may decrease suddenly. So who will take care? Similarly things may be like we may have a large size of solar generating ramping, so which occurs like as large cloud passes over it, like the complete or the like we may have 100 megawatt of the solar power plant, and suddenly the 80% or the 70% or the 100% solar power plant is covered with the large clouds, so the sudden generation will suddenly decrease. So ramping may be increased as variable resources are added to the grid. Okay. So if the ramping does become significant, then system operator will have to respond or the grid could become unstable. If these things suddenly generation increase or suddenly load increase or suddenly cut out of the outage of a particular plant, that may be the cause of frequency and voltage variations in the grid, or we can say power mismatching. Power may not be in a limit, and that may be the cause of blackout as well. Now frequency regulation, so microgrid can come into the picture here again. So when the supply exceed the demand, like the excess supply, so frequency regulation down is needed to offset the discrepancy. And based on that, here we can see that this is a like power, and we have a demand curve here, which is represented by the brown lines, and we have a supply. Okay, so here we have a less demand, the demand generation is fixed, like for example, so here who will take care of all these things? Okay, in case of traditional power plants, and the parameters are changing in seconds. Okay, so now the things has been further changed or become more dynamic. So like the variable renewable generation is there, this is our ramping sources is there, and this is net. Okay, so ramping source will take care about the uh, variations in the renewable energy resources. If the here is the generation is less, so this ramping source will take care. Here is the generation is high, it will start charging, discharging, and so on. Now, so if we are talking about the behavior of the various power plants, so battery equivalent circuit diagram is shown in this figure, and the battery characteristics is like this. It means like the maximum allowable recharge or the charging capacity. It's not like if we have a 100 kilowatt or ampere hour battery, so they are based on their characteristics, we cannot consume the 100 ampere hour at or we cannot discharge that particular battery within 1 hour. That may be the further losses As I hope if you have the electric vehicles or the manufacturer of the vehicles, they are saying they have a multiple modes, eco plus, eco, normal, and a sports mode. So basically that is designed for the like normal and eco modes. But if you are discharging the battery with the fast rate, that may be the cause of drastically reduction inside the backup period of the battery of the electric vehicles. Okay. Similarly, if you charge the electric vehicle with a faster rate, so that may be the cause of uh, small life of the electric vehicles battery. Okay, so this here we can see how the percentage, like the desktop previously discharged, like how the things will be 45 to 100%, and the times required and ampere ratings is there. If we talk about the energy management system for multi-terminal DC microgrid, so this is one of the case studies I have also done. So microgrid with the lamp load. Here we have what we have considered. We have a this is bus is there, and we have the multiple battery bank is one, battery bank is two. So basically, as I mentioned here, the power exchange with the battery is based on their characteristics. So most of the users, they provide their battery characteristics. Okay, so with this characteristics, we may decide, or the system may decide, that how much charging and discharging rate should be of that particular battery bank. Okay, so to maintain this state of power exchange with the grid, this is the intelligent energy management system I have developed during my research. So here we have a current sensor which is monitoring the current exchange with this grid, and we have a power electronics converter here, and then PWM pulse. So this is the voltage sensor which is giving information that either the energy power is required, or power like the voltage is higher or lower. Based on that, the system may decide that either the power should feed into the grid or it should be consumed from the grid. And based on that, both the controllers will be like controller 1 and controller 2. This is controller 2 is also has the reference value from the state of like the SOC of the battery, so that it can select take the actions. And based on these two, the minimum selector will decide the minimum values of the output of the controller 1 and output of the controller 2, tau 1 and tau 2. So whatever the minimum, that will, based on that, that will activate the PWM pulse to control the power exchange, and the remaining power, remaining things will be transferred to the another source here. Similarly, still this controller also have the characteristics of battery bank 2, and based on that, so battery bank may be two different types. One may be for the long time, and second one may be for the short duration. The another case studies also we have done in this, in the same paper, like the distributed load and distributed gen. So this is the one way to, first one is uh, increase the battery efficiency by the by changing their by controlling their charging and discharging rate. The another one is here, like how we can shift the selection of the closest source. Like for example, if we want to supply this house one or home one, so which source should be selected? Either it should be supplied with this battery bank or this solar power plant, or it should be yeah, so lamp load is means we have considering the load is at particular constant at particular location only, not load is not distributed. Load is we have a large structure, and this complete structure is supplying one industry which is connected with this grid. But in this case, we have considering, so for example, one industry, as I mentioned here, like we have a battery storage, we have a PV system, we have the public utility, and we have some machine, large, like some uh, um, industrial machines may be there, or some industries there, like the cement plant or the chemical plants. Okay. Narendra, yeah, you can ask the question, please. You can unmute yourself and ask if you have still doubt.
Sir, all the participants are muted. I will unmute him in the last if he wants to.
Okay, okay. Okay, thank you. So now another one is the like microgrid distributed load and distributed generation. So here we have considered that the load is connected to one term at particular one terminal. Here we are saying this is a ringman system, and the load is also distributed, like home 1 is here, home 2 is here, home 3 and home 4 and so on, like this. And we have the community level PV power plant, we have a utility connection with this microgrid, and then we have a like different energy storage devices. So based on like battery bank 1 and battery bank 2, so like if this is the home only, we want to supply, so which source should have the priority? Okay, so like based on that, why we are going for it, because we want to reduce the energy losses or the power losses in the lines by selecting the closest source. So like to supply this home, so first priority will be this battery bank, and the another may be like the based on the distance, like maybe the solar power plant or maybe the utility based on the distance. Like for this home, the this PV power plant is the closest one. So in this way, the line losses can be optimized. So here I have just considered an example, the power line losses minimization using the closest source. So here I've considered like load 1 and load 2, RL1 and RL2, and two switches S1 and S2 are connected. And this is the cable. Here we have considered the two sources U1 and U2, and their internal resistances are RD1 and RD2. Okay. These are the system parameters. So here if we supply the like load 1 with this U1 source, and if what will happen if we'll supply this load with source 2. So in the first case, if we supply this load with this source, only their internal resistance will come into the calculation, or maybe the cause of losses in the lines. But if this load 1 is connected with the source 2, it means their internal resistance of the source 2 as well as the cable resistance will come into the picture, because the cable resistance means the cable required from source 2 to the load. Okay. So with this, like the proposed uh, intelligent energy management system in case of the lamp load, just objective was to maintain the state, maintain or to follow the characteristics of the battery bank, so that the heating problem may not be occur inside the battery, or the cooling required for the particular battery may not may remain in the optimal level, and in this way the battery backup can be increased, or can get the actual battery bank backup which is claimed by the company. Here we can see the large exponential losses, because the losses in the lines will be I square R. Okay, so square times of the current is there. Okay, so the small exponential power losses is like with the, if the current is like here, we have considering the I1 source 1 current, and here is the I2. Okay, so if the current partial current is supplied by the source I1 and I2 is the current source, so here the voltage drop. So it will not only cause of the losses, it will also the cause of voltage drop, because if we are considering this is a like 10 km far from the source, this is one source which is just close to the load, and this is 10 km, yeah, 1 km or 2 km like this. So the cable resistance will, and because of this cable resistance, the voltage drop will also occur. Okay, so here we have shown the study of the power loss, power losses as well as the voltage drop with respect to the value of the resistance of the internal resistance as well as the line resistance RD1 and RL1. Okay. So case study of this distributed case like distributed load and distributed generation. So here we have considered the 4 houses, home 1, home 2, home 3 and home 4 is there, and the total like power at different with the previous one and the current one, okay, like with the proposed one. So here like we have this is representing the red line representing like the PV generation, then building demand, green line, and then battery power and public utility power, like power exchange with the grid is there. So here we can see like in the previous case, the losses were here it was like the red line is representing the previous losses, and with the selection of the closest source, we can see that the power losses has significantly reduced at different time instant. In this time instant, the power in the night times, because the load is supplied with the utility only for all the houses, so therefore the losses remain same, but rest of the time when the load is supplied by the uh, solar power plant and the battery bank, the losses in the lines has been reduced significantly here. Now the question is comes like we have talked about the distributed generation type of microgrid systems, and we have discussed about the lump load based like we have a multiple generating stations, but the load is at particular connected at particular location. Okay, so now the question will come, which type of microgrid should be? Like it should be AC microgrid or the DC microgrid. Okay. So if we talk about based on this, based on these parameters, we may decide like which may be the more suitable for particular application. So like DC energy resources, if we talk about available in the market, like so renewable energy resources, either solar, wind, or small power plants. So these are either DC in nature or DC compatible. Second one, if we talk about the storage, so battery or electric vehicles is also the battery or other storage devices. These are basically DC compatible or DC in nature. So battery is basically storing the DC. Now, if we talk about the lightning loads, so LED is 10 to 100 times more energy efficient as compared to the tungsten bulbs. And because of this, you will never found a tungsten bulb in any residential building. Either they are using the CFL or they are using the LED. The CFL is neutral to AC or DC power, okay? And the LEDs are DC in nature. So we have the generating station DC, storage is also DC, and load is also DC. If we talk about the other loads, motor based, so a small DC motor can be 2.5 times more energy efficient as compared to the uh, AC motors. Like if I give an example of a uh, uh, ceiling fan. So ceiling fan, if we go with the BLDC based, so the power consumption is around 20 to 25 watt, while the induction machine, single phase induction machine based ceiling fan, the power consumption is around 70 watt. So that's the various things we can see with the DC technology. And if we talk about the previous problems why the system were not designed for DC only, so the brush replacement was the problem, but with the BLDC and permanent magnet base, that problem has been sorted out. If we talk about the other things like other appliances installed in the residential building, so that it may be the fan is primarily a motor, so DC can also be the better control for the DC type of appliances. DC systems has better control. Then if we talk about the appliances, refrigerator, air conditioner, washing machine, grinder, etc., all are basically motor. So it can be changed with the DC technology. Okay, if we talk about the electronics load, like all electronics, mobile, TV, computer, etc. These are low voltage DC appliances. And these devices, these appliances required the need of AC to DC. If we have a AC distribution system in the residential building, it means we require the converter to connect the DC appliances with the AC distribution system. And their efficiency here we can see they have the small transformers inside it, 909 or 606 and so on. So and their efficiency is 70 to 80% only. It means we are wasting the 20 to 30% energy in the conversion only. So does it make sense? We have the DC storage, DC generation and DC appliances, and even these appliances are more energy efficient than why we are converting it. If we talk about the other advantages of the DC system, so DC system require only 2 conductors and DC system no inductance. So because of no inductance, the voltage drop in the DC system is less, and the voltage regulation is better for this. Now the absence of the capacitance, because this is based on the frequency, so less power losses will be, and because of there no need of to charge and discharge the capacitance of the line. Okay, so now a DC system require less insulations than a AC system because of less potential stress, because the DC system work on the peak rating and while the AC system work on the RMS. So that's why less insulation is sufficient. DC system has no skin effect. So we can utilize entire cross-sectional area of the line conductor. It means that more cross-sectional area is utilized. It means the R equals, we know R equals rho into L by A. So if the A is higher, it means the resistance will be lower in case of DC. Then DC system reduces the amount of resistance because of the complete cross-sectional area can be utilized. If we talk about the advantage of a common DC bus rather than the AC, so easy to enhance the system capacity, okay, by adding the additional DC power generating sources like PV, etc. Ripple management by adding the more capacitors in the DC bus. And then we have a high system reliability. So AC bus, like if the alternator fails, there is a good chance of circulating current flow through the alternator and there is a big impact on the system. So earlier that generator were working as a source, but now it's acting as a load because of the failure, the circulating. So protection is required over there. So in DC systems, like every power generating sources can be isolated using diode. Power diode is there. They can able to share the power independently. Blocking diode is there to prevent the power injection into AC system. DC system, it's a typing mistake, please. During both steady state and transient system conditions. No fault contributions or reverse power injection from the DC system into the AC systems. This is one of the case study I have done for the residential building. So here we can see in the traditional distribution system, we have the solar power plant, we have a battery, then we require the converters. These are our conventional appliances we have considered, and like fan, geyser, etc., air conditions. And then we have the electronic loads. So everywhere we can see we require the converters. So these converters are not only decreasing the system efficiency, as well as it's the system cost. Okay, but if we have a DC distribution system like here, we can connect the different loads, and if we require the variable voltage supply for based on the rating of the appliances, we may use DC to DC converters for particular bus or particular line. This is the case study. So here we have considered in this study we have considered the AC distribution system with AC compatible load, means AC technology based load like induction machines based or the tungsten bulb, etc. Then we have considered the AC distribution system with DC technology based load, means the BLDC, permanent magnet type of motors are used to make the particular appliances. And then DC distribution system with DC technology based load. It's a complete DC distribution system. And here we can see the PV panel rating in kilowatt. For first case, AC distribution system means the previous traditional system. Now hybrid, we are using AC distribution system, but DC loads we are using. So the panel rating has been reduced significantly, and further if we'll go for the DC, then how much the panel rating can be reduced. Number of batteries, this is also an important parameter. So here we can say the battery size. So as the size of the battery as well as the panel is reduced, it means we can say that the system uh, capital cost can be reduced significantly. These are the possible energy saving from most efficient DC internal technology based appliances. Means the appliances used inside the residential building, they have total energy saving with DC technology, and the appliances power consumptions and AC DC conversion efficiency at different time for the different types of converters used. So based on the AC/DC, their efficiency is listed here and their power rating is also here. For this case study, how we have observed it, this is like AC distribution system with AC appliances, AC distribution system with DC appliances, and DC distribution system with DC appliances. So here we can see so how the power curve or the power demand curve has been reduced with the DC system with DC appliances, shown by the green line here. Okay, this is for the battery power. So we can say the stress on the battery is also reduced significantly because the energy demand, power demand curve has been reduced significantly. Okay, then if we talk about the power consumed from the utility, of course, if we have a small size, like if we need to run only the 5 DC bulb, DC fan of 20 watt, 100 watt is only the consumption, while in case of AC appliances, AC fan, we required around 350. So definitely we can see same thing here. And then if we talk about the conversion losses. So in the traditional AC distribution system with AC appliances, so we can see here the red line is representing the conversion losses. And then because these conversion losses are because of the converters required at the battery end as well as the converters required at the PV systems. Then we have the AC distribution system with DC appliances. So these converters are converter losses at different time instance has been changed. And then with the DC distribution with DC technologies, so in this case, because we have all the sources are DC and DC loads and DC bus, so conversion losses has been reduced significantly. So here we log conversion losses in the appliances, internal converters. So here we can see that the green line is just flat here, means no converters or very small amount of conversion is there. So conversion stages, if we talk about the energy demand for all three cases. So in case of AC technology, AC distribution, 27.93 kilowatt hour is the energy demand for a 24 hours. With the second case, it's 12. And with DC distribution system with DC technology, it's 11.12. And based on that, here we can see the conversion loss is reduced significantly, 10 times approximate. And the total energy demand of the house is 32 to 11 only, or we can say around 33%. Means the only 1/3 power demand is there with the DC technology. Then PV size has been, and the PU size also reduced significantly. So number of conversion stages with DC technology has been reduced, energy demand reduced, converter losses conversion stages has been reduced, and the distribution system requires small size of PV panel and battery bank and less stress on the utility. Now, next one is like the microgrid system case study for integration of photovoltaic and electric car at real-time electricity price based. As I have mentioned, like different uh, sites like the real-time price based or the fixed based. So in this case, I have considered the real-time price based. How the system can act. So in this, like the conceptual layout of the DC microgrid for a residential building is shown here. We have the complete DC load here, washing machine, CFL, exhaust fans, and submersible pumps. Then we have air conditioners, LED bulb fan, and other cell phone, etc. Here we have a coffee machine, etc. So these are the various appliances. Then we have a control unit which is more connected with the different generating sources like public utility and the internal source like solar rooftop mounted solar panels and the battery bank and electric vehicles. And the user is using their all assets like battery storage as well as they have introduced the energy management with the electric vehicles. So vehicles will be charged or discharged based on the electricity prices. Okay, so the this microgrid will completely utilize their internal sources to optimize the electricity bill of the public utility. So here is the control algorithm for this data collections from the PV and building demands and then calculation of the microgrid price, because these microgrid price are used to trigger the appliances on and off based on that. The another input will be the like user comfort is there or the information fed it by the user to complete the particular task. So source management, like the selection of the source, like either the battery should be start discharging or it should be in the isolated mode or it should be in the charging mode, and then the power consumption from the solar will be maximum, and then the power exchange with the grid, like either it should act as a load or it should feed it to the like it should consume the power from the grid or it should feed it to the grid. Okay. So here we have, this is the curve of the PV power plant generation and then the electricity prices for a typical day. And the mode is like mode one is public utility and the electric energy storage as a source. Like the battery is supplying to the grid. So public utility plus battery, both are supplying to the load of the building. So the equation is like here, and the battery prices are considered 4.39 rupees, and while the utility prices are varying from 4.8 to 4.6. So based on that, the which how much power should be consumed from the grid and how much power should be supplied by the battery wing is shown here. Then we have the second case is like the public utility as source and energy storage as load, means energy storage in the charging mode. Then how it will be. So here we have shown the hybrid car power for manual and automatic control, means manual control means whenever you will come and you will connect to the grid, and then if the control of the appliances is based on the electricity prices, how it will charge and discharge their phenomena is shown here. If we talk about like the photovoltaic system, solar system, public utility and energy storage acting as a source and they are supplying to the load. So here we can see like the in case of automatic control, the demand is always less as compared to the manual control mode. Now, if we talk about the PV and storage is there and they are supplying. So at different time instant, like here it is mentioned like the prices are, the rating was like 4.73 kilowatt to 0.9 only during the 18, somewhere here we can see, and during the 17. So here we can see like the battery is how the battery is a hybrid car and the batteries are supplying to the grid. Okay, Then PU power exchange with DC microgrid. So the PU is public utility power exchange. So here we can see like the manual controls, sometimes the power, but here we can see that in case of automatic control, the power exchange, when the prices are high, that time the like here 10, 11 to 17 here during this interval, most of the time the PV is greater than the sum of the building demand and ES power. So the microgrid prices remain fixed at 3.82, and therefore the load is supplied by the PV only, and the balance PV power is either stored in the store energy storage or feed it to the grid as shown is here. Sometimes the feed it to the grid and sometimes consuming the with the internal. So here we can see the building demand, how the building demand shift from traditional mode to the automatic. So here we can see in the night times when the only the grid is supplying, so the demand remains same. But here in the morning times, we can see here in case of automatic load control, in the traditional system, the demand was here, but now it has been shifted here because of that time the prices were a little bit low, and here the demand is when the generation is there, electricity prices, grid prices are high, that time the automatic control shift the load from this time interval to the here. Okay, so in this study we found like the microgrid by approximately 19% lower energy from the utility at 5.4 lower electricity prices. Okay, the microgrid sells around 4.5% higher energy to the public utility at the 2.23 higher electricity prices, and the battery bank and hybrid car received 11.2 to and 15.36 profit in the energy cost. If we talk about the overall electricity price, so building electricity bill around 6.12% as compared to the manual control. So it's reducing the energy per kilowatt because the energy consumptions inside the building remains same, but by shifting from peak to the lower, so the per unit cost has been reduced, and because of this per unit cost, the electricity overall bill has been reduced 6%. Now this is the another case study done by my students, like microgrid case study, AI enabled vision based. So till now we have discussed about like how we can shift to the with the same amount of energy demand, how we can optimize the size of the distributed generations like solar panel, battery bank, or how we can optimize the electricity bill. But we didn't talk about the energy consumptions inside the building. How can we optimize that one also? So in this system, we have developed a AI-enabled vision-based building automation system, which can which can identify the location of the occupant inside the building, and based on that the closest appliances, tube light or the fan will be operated. So this system is developed for the academic buildings in our institute. So here we can see this is one classroom we are considering here. So AI enabled vision based, we have a camera. So camera is continuously clicking the pictures here, and we have a Raspberry Pi system to interact with the relay module and the camera. And this paper is published in IEEE conference on by the GBU Greater Noida in just last week. So here this camera will click the pictures, and based on the location of the coordinate, it will send the control signal to the appliances, tube lights, and the fan to either keep it on and off, because this is the main because of the manual control mode or the other control things which are based on the like PR sensor based or the other IR sensor based. So based on that, these sensors like the appliances are remain on either the occupants is there or not. Okay, so for this we have used the, generally people use the SGD based uh, optimizer for the training optimizer. So it was the efficiency is 50 and the accuracy was 50, and the if we talk about like 40 to 42%, while the we have used the atom optimizer used in the proposed model. So training is like 100%, tuned 0.001, and the accuracy was 95% here. This is the formulations about the how the things has been used to train the system. So here we can see like the this is the one object, and the lights is shown here. Here I've tried to show the uh, like the virtual things, how the things has been done over there. So this is the location of the head of the occupants, and their location coordinate has been identified, and based on the coordinates of this and coordinates of these appliances, the system is able to find out which is the closest appliances here. Okay, and then this is the virtual things, and that then this location is converted into the actual metric, like in the meters actual distance of the particular appliances. So here we can see like the distance of the system is automatically monitoring the distance of particular appliances from the object, and it shows that the why this light is on in this case, because the green, this is the closest tube light and this is the closest fan to this object. So that's why this fan is on and this tube light is on. The rest of the things are remain closed. So in this way, basically, if the one student is there, or the students are sitting in a group of students are sitting in group at particular location of the room, the rest of the appliances will remain switched off. While generally we can find out in our academic buildings, most of the appliances remain on. Either the class is completely occupied by the student, or only the few students are sitting. Even the no a student inside the class, still appliances are going on. So in this way, this approach is able to optimize the use of energy consumption inside the building. Okay, or we can say the energy demand of this system will able to optimize the energy demand of the particular building. Okay, so here the similar type of case studies has been shown, because in previous case I didn't show the virtual things like the tube lights was open, but now here the system has identified these are the closest thing for this, and the lights, relative lights has been switched on and the fans has been switched on. In this case study, like the uh, different fans we have considered here, to 8 fan in this room, and the tube lights are there, 5 tube lights on the wall, L1, L2, L3 and L4, and the ratings is listed here. Distance from the target occupants, so fan 4 like 4.87, and the light tube light 2 6.55. So these two are in case of the appliances state. If we talk about the manual systems, so the remain all will it will remain the active, while in case of the proposed systems, the only the this fan 4 and the light 2 tube light 2 will be active, remaining will be the in the off state. Okay, so we can see that at particular time instant the power uh, generally remain 800 watt, it has been reduced to 115 watt only. So this is the classroom time versus power curve for particular day. So here in case of with the proposed system, generally then this is these bars are representing the number of occupants inside the class, or number of students in the class at different time instant, because the number of students vary with respect to the class, like subject as per the timetable the class may be there, or the specialization class may be there. So generally the students around 60 for the core courses or the regular common courses, but for the specialized courses the students are varying. So how with the as the students are varying, their power demand consumption is also varying here. Okay, while in the always at peak, but here as the number of students are changing, the uh, power curve is also changing accordingly. So proposed system can identify the occupant location, and both the beauty of this system is like we have the in the literature you may find out the other type of automation system also, but both they are not applicable for the static and dynamic cases of the occupants. We can either count the number of persons enter inside the room or they are sitting. If they are in a standstill mode, it's considered that there is no object. So it will affect not only affect the power consumption as well as affect the user comfort. If we were with the proposed reduce the significantly around 85% at particular time instant. And if we the another thing is because we are just gathering the information or extracting the information from the captured image, which is all like the from image captured by the CCTV, which we can generally find out inside the classroom. So we are not adding the other more complicatory circuits. We are just extracting the information from there using the engineering tool, mathematical tools, and based on that only the relays will be activated. So very small things will be changed. Means the complex circuitry number of sensors can be has been reduced with this proposed algorithm. Okay, so this is the case study. If time permit, I can go with the another one, or should I stop it here?
Continue.
Okay, thank you. So another case study I have done is microgrid system case study for integration of photovoltaic and energy storage for Iceland sites of the utility. Means we have considered a system or a house which is very far from the grid, not connected with the grid, but the utility want to electrify that area. So the microgrid, Iceland microgrid may be installed over there. So what will happen and how the things can be, how we optimize the size of the sources and how we can utilize them in an efficient way. So this is a autonomous DC microgrid for buildings. This project was funded by the government of India and the government of UK, United Kingdom. And there were 3 universities involved in this project. One is IIT Mandi, second one is IIT Kanpur, the third one is University of Loughborough from UK. Okay, so in this, what we have done, we have a manual control for all the one another thing I would like to mention here, like all the appliances are DC in nature here. BLDC fans is there, and we have the LED bulbs, DC converter, tube lights is also DC, and we have make a like simulator for the differable loads and cycle based load, like for the refrigerator, washing machine, and water pump. Okay. This is our electronic switches to automatically control the appliances. And we have the current sensor and voltage sensor to measure the line current as well as voltage at different time instant. This is our battery bank, and we have a photovoltaic power plant. The conceptual layout of the autonomous system is shown here. We have 8 panels of solar, then we have 4 batteries, and we have the 2 solar charge controllers, and 2 buses are there. One bus is like for few fans are connected with this, and tube lights and few LED bulbs and everything. Okay. This system also has the SD card readers to log the data for the future use and timer circuits to synchronize this data with the global clock. And then we have a manual control switches, which are also showing connected with the system, and LCD display, which are showing the voltage, current, state of charge of the battery, etc. All the electrical parameters of, and as well as it's showing the state of the different loads. Okay. The good thing is a single energy storage unit in which we have the four energy storage, but they are the terminal of both the solar charge controllers or the controllers is common for the battery terminals. The good thing is, like, if the one of the charge controller will not work, means one of the load of this solar charge controller will be cut, so this power can be fed it to the bus, to the storage, or it can be fitted to the another charge controller to supply the load connected here. Okay. Similarly, if this controller will not have any load, so the power generation with this plant can be fed it through this to the either energy storage or fed it to the this. So in this type of cases, like how you will calculate the size of the PV power plant. So the PV watt hour needed for the power losses in the lines. As I mentioned earlier, the total power means loads generation is equals to the losses plus actual consumptions. Okay. So it will decide the watt hour needed per day from the PV panel. Okay. Now the losses may be like the energy losses in the converters at the source and load end, or the energy losses in the lines in cables, or energy losses in the energy storage unit. As I mentioned, because battery bank has their own electrical systems, so it doesn't means like if you feed it like 100 ampere hour inside the battery, if the charge is fed, then we cannot extract the same amount back to the to supply it, because because of their internal circuits there will be some losses. Okay, so that losses is also considered in this system calculations. Okay, now the size of the PV plant depends on the watt hour needed from the PV plant and the number of average sun hours per day in a whole year. So it's like if you are calculating the system PV size in the month of June, so the time span will be different. If you are talking about the 30th of December, so the time span of the day will be different. So in this case study, we will consider the average sunny hours per day in a whole year. So like in out of 365 days, what will be the average sunny hours if we calculate for complete cycle? Okay. So PV power plant size, watt hour needed per day divided by the average sunny hours. So it will give you the actual size of the PV plant. Then battery bank capacity we need to calculate. So battery size should be large enough to store the sufficient energy to supply the load in the non-sunny hours. Okay, or in cloudy days. Like we may have a particular size of PV plant, we have a battery bank, and if we have designed like the battery bank is sufficient enough to supply in the night hours, because in daytimes we will have the solar systems. But what will happen if some raining season will be there or some fog season will be there in like in the winter in India, especially in North India, we will find out a lot of fog and we are not able to see the sun for 2 and 3 days. So that type of situation we need to also consider when we are calculating the size of the battery bank. Okay. The another thing is like what will be the depth of discharge of the battery? Either you will discharge it up to 0%, 20%, 25%, 30%, whatever. So based on that, that is also. Then the total uh, load we need to supply through the battery. Okay. And this is representing the annually total number of non-sunny days. Then the another parameters, because for the backup period, we need to know about the state of charge. Okay, state of charge of the battery. So it's the ratio of current capacity to the nominal capacity. So state of charge can be like with respect to time divided by the total capacity. We can say how much percent is the SOC can give the how much ampere hour left inside the battery. If we talk about the calculations, like how we'll get the like what is the value of uh, like the state of charge at particular time instant, how the so there are different method. One is called open circuit voltage, and second one is like Coulomb's counting method. There are other methods also, but in this system we have just used the simple mathematics of Coulomb's counting method. So if you want to calculate the state of charge at time instant t, like at for example 10 o'clock in the day, so we'll just calculate it. We will check the state of charge just previous hour or the whatever the time step we have considered here, plus the charging current, which we can get it from here because we are monitoring the current. Okay, and then the total capacity of the battery and multiplied by the time step size. Okay. In this system, why we have considered the DC system, why not the AC? So here we can see the cost with this small system like PV plant. So we require the power. DC is nature, so type of converters DC to AC. If we go with the traditional systems, is required and their cost is around this much. If we talk about the load end converters, so this is the cost. So with the DC technology, we have saved the like converter cost inside the converter. 18 converters has been removed and their capital cost around 16,000 is also decreased. If we talk about the control algorithm, so in this we have considered the different, we are monitoring the system is monitoring the power generation from the PV power plant and the state of charge. So state of charge, we need to regulate, we need to maintain the state of charge of the battery to supply the critical load when the sun will not be available. Okay. So this algorithm will compare the state of charge measured and state of charge desired at particular time instant. Okay. There may be like peak time of the solar, but that time like the load is also there, but battery for the first and then go with that to supply the other loads, because the critical load need to supply when the sun will not be able. So then it will calculate the building load PV. So if the power generated with the PV panel is less than the building load, so it will ask for the, and the measured is SOC measured is less than that, so it will ask for the battery to charge the battery first. And if this is not the situation, then it will say to operate to keep the battery either isolated or to discharge to supply the load. Okay, so here now the delta P is the like variation in the power generated with the solar power plant and the building load. So PV minus PB plus PCL, and then it's PNCL means this is critical load, PCL is representing the critical load. Okay, so here non-critical loads, if this is delta P is less than non-critical load and greater than or equals to the deferrable load, so it will say not to switch on the deferrable loads. That may be like refrigerator, cycle based. It may reduce the operating cycle or may change the thermostat setting of the refrigerator. And then the another constraint will come here like deferrable load. If yes, then their time required to complete the task and task completion time, like washing machine may require 1 hour to clean the clothes, and the task user may feed it the information, okay, the task clothes should be cleaned before 3 p.m. Okay, so the system will check, okay, it's 2 p.m. and I have a surplus generation. either which appliance should I on, either I should switch on the pump or washing machine. So it will check, okay, as per the user, the washing machine should clothe the wash before 3 p.m. Now 2 p.m. is there. So I have to give the first command to the washing machine to switch on and keep the water pump at hold. Okay. Maybe like it may be reverse, like the first water pump may be required. So based on the user information, this system will automatically switch on and off the things. Okay. So based on that, either the battery will charge or not charge, or different loads will be on. And this project, we got the 2 patents for this project granted in India, as well as 1 paper in the conference and 2 papers in the 1 paper in journal, Sprint Journal also. So refrigerator cycle-based load, like a regular cycle-based, so operating time 30 minutes. For the Whirlpool refrigerator, I'm monitor this data. For the regular cycle, the operating time is 30 minutes. Off time is 80 minutes. In the control mode, 15 minutes, and 80 minutes is the off time. So off time will remain same. Operate based on the control and regular cycle, the operating time will change. So in this way, the energy consumption to run the refrigerator may be changed. Okay. Water pump, differable load we have considered. Either you can switch it on during the day times or the evening times. So system will automatically operate it whenever the sun is available. At that time it will fill the half tank, and then in the rest remaining slot it will fill the another half tank. Then washing machine. Washing machine is like for 90 minutes we have considered in this, and washing machine task completion time is 1 p.m. we have considered. So how the load has been changed, like this is the PV curve, and this is conventional scheme, and proposed demand side management scheme is there. So here we can see in the morning times with the conventional system, the load was high, but the proposed system, based on the user input, it has shifted the load from here to keep the load low, because this time the load was run by the battery bank. And as the load is PV panel starts supplying the load, then it start increasing the load as compared to traditional. So green line is representing that the load is higher during the sunny times, and it will remain lower or equal during the non-sunny hours as compared. And the state of charge of the battery is also regulated. This is the desired value. Green blue line is representing. Red one is the conventional system state of charge, and the proposed one keeping the green line. So it's showing that our system will never be failed. It will always provide the electricity to supply the critical loads during all the 24 hours. It will automatically regulate the energy charge stored inside the battery. How we have achieved this state of charge? So here we can see like the state in this, the state of the controllable loads, like tube lights mounted inside the bedroom 1, 2, and living room and kitchen is there. And the another one is the control of the control cycle based on the cycle based refrigerator type of load, or the differable like refrigerator, washing machine, and water pump is there. So in the traditional system, here we can see the refrigerator work on a observed that the generation is not sufficient enough from the PV plant as per the previous days or in the past history, but now 2 days the sun is available for less hours, so it has shifted the refrigerator operation from regular to the control cycle mode. And here we can see the blue line is representing the control mode command or state of the control signal. As well as it has washing machines. So washing machine, generally in India, we can see like in the persons wash the clothes early morning, take the bath, and they start washing machine. But that time the sun is not at peak. It means what we are doing, we are consuming the system is consuming the power from the battery bank. It means the system required a large size of battery, and their power rating, sharing capacity should be large, their energy storage capacity should be large. It means we need to put a lot of capital money. So to minimize that one, the DSM system shift the operation of this washing machine from here to the here when the sun, like midday of the time when the sun is sufficient enough, and directly consume the power from the solar system to run the washing machine. Then the water pump has been also just started in the morning for few times. Then again it was started. It has been shifted from here to the around 10 o'clock, and in the in the afternoon it was again filled to the tank. While in the traditional system, the red blocks is representing that the pump were run during the early morning and late night, means totally run by the battery bank. Okay. So based on these study, we can find out here the conventional scheme with the DC technology based in, we have considered the DC technology in both the cases. So the energy demand was 2.7 kilowatt hour. Ampere hour needed from the batteries, 585 battery, number of batteries and PV size, and PV cost and energy storage cost 1,64,000. But after adding the demand side management, the energy consumption remains same because we have just rescheduled their operating time. We didn't cut the operating time or energy consumption. So energy consumption is still same, but the ampere hour needed from the battery has been reduced. Battery size has been reduced. Solar size has been reduced. Therefore, the battery and capital cost of the battery and PV system will also reduce. And here we can see at the place of with the conventional system, we need to the system cost is 1,64,000. Here is only 1,10,500 only. So the outcome of this complete studies, Microgrid provides an opportunity to use the RES power and electric vehicle at local sites with high comfort or in a good interaction with the grid. It can work an interactive and so it gives the more flexible connection with the utility. So Microgrid provides an opportunity to integrate the RES with the national grid. Electrification at remote areas. DC microgrid system optimize the conversion losses, system component cost. And after adding the demand side management scheme, we were also able to optimize the power losses, storage and their converters, and power source size and the system capital cost. Applications and opportunities. So residential and commercial buildings in remote areas like grid connected sites, poorly grid connected site, isolated site, whatever the possibility of sites in electrical systems, microgrid can be used. And the other applications may be military sites, agriculture sites, and integration of renewable energy resources in data centers. We may find out the microgrid case study over there. So with this, thank you very much. This is my channel where you can find out a lot of similar type of case studies, results published here. So thank you. Thank you very much.
Thank you so much, sir. To the participants, if anyone has any queries, they can message or they can ask for to unmute them. So one question is in a chat box. It is asking what is lamp load? Any example for lamp load?
So basically lamp load is we may have a one steel plant, for example. Okay. So in this, like if we want to cut something, so the size of the machine, that particular machine may be sufficient large enough that we are not able to supply that that unit single unit with the battery or solar itself only. We have a multiple loads and just one to supply that particular one unit. We have a multiple sources is there. So we can say like 1 point complete load is considered at 1 point only at particular one location.
Narendra, Itela Narendra, sir. Okay, I will unmute you. Just wait.
Yeah.
Itela Narendra, sir, I have requested you to unmute yourself.
Yeah, thank you. Thank you. Sir, it's very good session, sir. We are literally waiting for this kind of session for the past 10, 15 years. So in fact,
Thank you.
if
Thank you
this
very much.
technology get into the residential buildings, definitely we are the #1 country in the globe because all the utilities are confined to DC supply only right now. So
Yeah.
it's very good thing, sir. So I have a few questions that I will ask you one thing.
Yes.
You have given the case studies in the form of slides. Can we have the accessibility to go through in detail with any link available with your website or profile?
Yeah, my website is given here. On all the slides, you can find out www.rksworld.org.
Okay, sir.
In all the slides, it was mentioned with my name. So with this on this website, you will find out my all the publications or patents granted here,
Right,
and
sir.
you can find out all the books, everything over there.
So, and one more thing, you have given a few case studies, one of which one of it. I have one question in that. That is for a charge to establish a charging station. We need to can we have solar integrated with BESS and DC microgrid without approaching the discom?
Yeah, that's the last case study I have considered here.
Yeah.
Yeah, here. Even this one is also like we have a I'm glad to share this information. Like we have the first DC microgrid, working DC microgrid for the academic buildings in India now, and
Yes.
this is in the Albag Educational Institute. I am the principal investigator for this project, and this project was funded by the UGC grant commission.
In fact, I am the consultant for a few charging stations in our area, that is in AP state, sir.
Okay.
So what I observed, the deposits are very huge amounts, sir. Say, for example, to get a 200 kilowatt load, the deposits includes around 25 to 30 lakhs. Simply because the transmission line charges and everything will be put on the consumer score.
Yeah.
Yeah. To overcome that difficulty, we can try this as a model for our projects only. That's a great advantage for me to participate in this webinar, sessions.
Okay, sir. Thank you. So basically, there is the constraint is like we have we require the large size of infrastructure. That may be the cause of losses inside the system. That may be the losses inside the converters, and that if we are running the load or our load is based on the traditional. So as I have shown here, if we go with the DC technology. So this is the complete autonomous system, as you have mentioned, that can we go with the autonomous mode.
Yes, sir.
So this system is we have considered in this study is like a complete autonomous system. No grid interconnection is there. Okay,
Right.
and
Yeah, one more
can
question.
yeah.
You are talking about the simulation done by the team, right? What software exactly we can get into that, sir? Is there any for
This one
simulations?
you are talking this one the
Yeah,
slides one.
generally you come up, you have
Oh,
given the
okay. The simulation case study, I have used the MATLAB for that.
MATLAB only. Okay.
Yeah.
Thank you, sir.
I have also worked one case study which is not covered in this session at University of Manchester.
Okay.
So basically, they have asked me to develop a
building automation system in which the chiller, everything, cooling and heating all we cover up, as well as storage.
Okay.
And there we have used that battery bank to provide the ancillary services to the grid.
Okay.
So whenever like the surplus generation, that time it start consuming, start energy storing, and after that whenever the load is there, so they start feeding. So it was similar type of this study based on the real time price based I have used for the residential building. They asked to do the similar type of things for the commercial building in the University of Manchester over there.
Fine, sir. And
Okay.
can I have an alternate for diesel generator by placing BESS along with solar all the time, not at the peak loads or daytime?
Sir, yeah, like here, why we are going with the why not we are going with the demand side management here?
Okay.
So as I have shown here, this algorithm, I think is it visible to you?
Yes, yes, sir. It's visible.
So basically, what this algorithm is doing, it's monitoring. It will get the information from the user. Okay, just give me your task completion time. It
Okay.
will continuously monitor that and how much time is required to complete that particular task. For example, if a user want to wash the clothes or he want to fill the water tank. Okay.
Yes,
So
sir.
basically, what we are doing in this case, so we are shifting the load from one time instant to the another one. The energy consumption is still same, but the objective is to mitigate this peak demand. Here, I can show in the morning hours this was
Yes, yes.
higher, and because of that, the large size of storage is there. Okay, so just do the generation. And the another thing is as I mentioned here, I didn't show that slide.
Do we need
One
to?
another case study we have done here in the DC microgrid system, which we have installed at the Albag Education Institute, in which we have used the micro turbine based hydropower plant.
Right, right.
Okay,
Do we need to connect power analyzer at the PCC?
Which one?
For example, if I want to make a study for commercial building,
Yes.
I need to connect a power analyzer for 24 hours or 48 hours to get the data logging from the various utilities.
Yeah, that's possible here.
Okay, okay.
Yes.
With that, we can be able to simulate the load pattern and
Yeah.
accordingly we suggest.
So basically, generally, people talk about that the battery is eco-friendly, no pollution is there like other fuel generators. But there are multiple
Yes, sir.
chemical reaction inside the battery, and the gas are emitted. And what will happen after a certain amount of years, like after few years? So what will be happen for the raw materials of the or the waste of the batteries? So
Right.
to overcome this problem, we have used the water storage tank at the rooftop. We fill that tank with the uh, surplus PV generation. And in the morning and evening times, when the generation of the solar plant is not sufficient enough, that time we also require the water supply generally in the buildings, early morning times and evening times. Okay, so that project is a case study how we can fulfill the two demands same time, water supply as well as the electricity
Okay.
with the reproduction. Yeah.
Thank you, sir. Thank you, madam, for giving me an opportunity.
Thank you, sir. Thank you.
All the participants, do you have any other question?
Any other question?
Sir, in the chat box, there is one question, but it is very unclear. It is asking any software applications to control microgrid. But I think it's not a complete sentence.
Yeah. So if you want to do the microgrid case study in the simulation, and then you can go with the uh, MATLAB, or if you want to do something hardware in loop type of case study, so we can go with the
Opal RT or real-time digital simulator, we called it RTDS. And now we have RTDS in few of our premium institutions like IIT Mandi, IIT Indore also have the, and Jamia in Delhi, they have the Jamia Islamia University. They have real-time digital simulators. Their results are very close to the hardware one.
Hi,
So,
sir.
yeah.
Sorry to interrupt, sir. Hi, sir. My name is Deepak Upadhyay. Actually, I'm doing the study as well in MSc Renewable Energy and doing
Okay.
some live project in ADMS and dumps in Saudi Arabia, and I conducted a lot of project in India as well. So my question
Okay.
is, sir, have you done any pilot related to DSM program which is integrated with the DUMS application, distributed energy resource management?
Distributed.
Am I audible?
You are asking for the like case study for the some load
Yes.
and distributed generations is there.
Yes, yes. Case study for the DSM, especially any out of country study like Australia or UK.
So over there, in like in the Manchester, I have worked for the battery bank and the distribution or building automation systems. But in
Mhm.
India, I have done the like case studies for autonomous microgrid and the simulation type of this is it was hardware based, autonomous based, and the remaining was simulation based.
Does in India, sir, any microgrid is currently in working at the utility level?
Uh, Yeah, we can say actually there is a confusion with the persons about the microgrid. So I also called my universities acting as a microgrid. Why I'm calling it like this? Because we have a multiple solar rooftop solar mount solar rooftop mounted solar systems of around 500 kilowatt peak. Okay, and we have a around 100 kilowatt hour battery, and then we have a load of the university, yani ki labs and classrooms and offices, as well as we have a locality here, residential locality. So that is also connected with the same. And all these things has been done a single point metering with the utility. So the complete area is acting as a microgrid, because if the grid is not available, our system can run with their own sources.
Okay. So Icelanding mode is possible, right?
Yeah.
Okay.
And
Sir, I
this
work
case
with
study, yeah, pardon,
yes,
please.
I work with the MNRE project for the rooftop solar scheme, right? That time we
Okay.
think for the net zero or the grid zero assumption for the 3 kilowatt or 5 kilowatt consumer, but that
Hmm.
it's not possible due to the high cost. Then we think about the DSM program. So that's why
Okay.
I ask such practical scenarios. Can we do that in
Yeah.
implementation for MNRE or
So
something?
So one, as I mentioned, like that project I didn't cover in this presentation. We
Mm-hmm.
have a 48 volt DC distribution system, DC microgrid
Mm-hmm.
that is supplied by hydropower plant and solar system and battery bank.
Okay, sir.
Okay, and that is in running condition in our institute, and
Okay.
I'm principal investigator for it and funded by the UGC for it. So yeah,
Thanks, sir.
if this type of opportunity will be there, we will be happy to collaborate with the funding agency. We can expand that project and more results maybe get it.
Sure, sir. I will connected you, sir. I did a lot of project in India with the consulting firm like Deloitte, EY, with the ministries. Right now, I'm in Saudi Arabia, so doing the same kind of smart grid projects. Thanks, sir, for it's
Okay,
honor to connect you. Thank you, sir.
it's my pleasure. I hope you have my email ID and website whenever feel free to.
Yes, sir. Definitely, I will connect you. Thank you. Thank you, sir.
Okay, sir. Thank you. Any other questions to you guys?
There is any other question? One can ask in chat box or can ask to unmute.
So I think there is no more questions. So with this, we end our day 2 talk, and I'm very much thankful to Dr. Rajiv Chauhan that you have discussed in detail various case studies related to DC microgrid and even experimental work. So I'm again once upon thank on the behalf of EICT Academy MNIT to deliver this talk. Thank you, sir.
Thank you. Thank you very much, Dr. Manmohan.
Thank you.
Thank you.
So with this, we end day 2, and we will be meeting tomorrow 2 p.m. With another experts on day 3. Thank you. Thank you all.
Thank you.